This video is brought to you by mywayteaching.com.
Now let us see another important part, the speed of a traveling wave. What is the speed of the traveling wave? So in order to determine the speed of this propagation of the traveling wave, we can fix our attention on any particular point on the wave. So we must choose a point on a wave. And then we should see how that point moves in time. It is convenient to look at the motion of the crest of the wave. It's very easy if you just look at the crest of the wave. You can see in this particular figure, it gives the shape of the wave at two instants of time for which differ by a small time interval delta t. They have observed this crest to see the points. The entire wave pattern is seen to shift right, that is in the positive x direction, by a distance that is delta x, isn't it? In particular, the crest shown by this cross moves a distance delta x. This crest, it moves a distance delta x in time delta t. The speed of the wave is then given by delta x by delta t, and we can put the cross on a point with any other phase. It will move with the same speed v. The motion of a fixed phase point on the wave, it is given by kx minus wt is equal to constant. This is the motion of the fixed phase of that particular wave that we just saw in the figure, in this particular figure. Thus, as the time t changes, the position x of the fixed phase point must change, isn't it? The point also changes. Here also you can see this point is changing from here to here, so that the phase remains constant. Thus we can write kx minus wt is equal to k x plus delta x minus w t plus delta t, or in other words we can write k delta x minus w delta t, which is equal to 0. Taking delta x delta t vanishingly small, this gives dw by dt. We can write dx by dt is equal to w by k. So relating w to t and k to lambda, we write v is equal to 2 pi w by 2 pi k, multiplying and dividing 2 pi. That gives lambda into v. That is also equal to lambda by t, isn't it? And this one we call it as equation A, and it is a general relation for all progressive waves. It shows that in the time required for one full oscillation by any constituent of the medium, the wave pattern travels a distance which is equal to wavelength of the wave, isn't it? And it should be noted that the speed of a mechanical wave is determined by the inertial and elastic properties of the medium. And the medium determines the speed. And this equation A, then it also relates wavelength to frequency, isn't it? Here lambda and v, how they are related, that also we are seeing. For a given speed, the medium can support both transverse as well as longitudinal waves, which will have different speeds in the same medium. Okay, this is the speed of a traveling wave, isn't it? Yes. Now let us study speed of a transverse wave on stretched string. Speed of a transverse wave on a stretched string. See, the speed of transverse waves on a string is determined by two factors. When you are considering a stretched string, on that the speed of the wave, that to transverse wave, it is determined by two factors. The first factor is that the linear mass density or mass per unit length, mu, and the second one is the tension T in the string. It depends on the mass density as well as the tension. Okay. And the speed of the mechanical wave is determined by the restoring force which is set up in the medium when it is disturbed, and even inertial properties, that is nothing but mass density of the medium. And the speed is expected to be directly related to the former and inversely to the latter. Okay, for waves, if you consider waves on a string, then the restoring force is provided by the tension T in the string. That restoring force is nothing but tension of the string, tension force. The inertial property will in this case be linear mass density mu. Okay, this is the inertial property, which is mass m of the string divided by its length L. And using Newton's law of motion, an exact formula for the wave speed on a string can be derived. But we'll not go for that derivation. We use dimensional analysis, and we already know that dimensional analysis alone can never yield the exact formula. The overall dimensionless constant is always left undetermined by this dimensional analysis. Here, first we'll take the dimension of mu, that is linear mass density. The dimension of this mu is given by m L raised to minus 1, and the dimensional value of this tension T in the string is given by m L T raised to minus 2. And we need to combine these dimensions to get the dimension of speed v. So when we combine these two, we get the dimension of speed v, which is given by L T raised to minus 1. So when we combine these, we should combine these two with this dimension of v. So that is given when we combine, we get thus if t and mu are assumed to be the only relevant physical quantities, then we can write v is equal to c square root of t by mu, where c is the undetermined constant of dimensional analysis. In the exact formula, it turns out c is equal to 1. In that case, the speed of transverse waves on a stretched string is given by, yes, it is given by v is equal to square root of t by mu. Okay. And here you should note important point is that the speed v depends only on the properties of the medium t and mu. It does not depend on wavelength or frequency, isn't it? It does not depend on wavelength, or even it does not depend on frequency of the wave itself. So of the two parameters, that is wavelength and frequency, the source of disturbance determines the frequency of the wave generated. Given the speed of the wave in the medium and the frequency, if in the question if they have given the speed of the wave, and even if they have given the frequency, then we can calculate the wavelength lambda using this formula. Okay. Now let us see a very simple problem. A steel wire 0.72 meter long has a mass of 5 into 10 raised to minus 3 kg. If the wire is under a tension of 60 Newton, what is the speed of the transfer waves on the wire? So using the concepts that we just discussed, you know we should solve this problem. So first here we should calculate, we know the formula to find the speed of the transfer waves, that is given by square root of t by mu, isn't it? And they have given the tension, the value in the equation, that is 60 Newton, isn't it? But we don't know this linear mass density mu. So we should calculate that mass per unit length of the wire. Mu is nothing but mass per unit length, isn't it? Yes. So we should calculate mass per unit length of the wire. So that is mu. So they have given the mass as 5 into 10 raised to minus 3 kg, and they have given the length as 0.72 meter. If you simplify this, we get mass per unit length as 6.9 into 10 raised to minus 3 kg per meter. So now we got the value of mu as well as t. We can substitute both the values in the given equation to find the speed of the transfer wave. So that is given by t by mu. So T is 60 Newton and mu is 6.9 into 10 raised to minus 3 kg per meter. So if you simplify this, we get 9. The unit of speed is meter per second. So this is the solution.